Okay, I have asked you guys to watch some other videos, and I've also asked you to read the book. But I want to give you a little bit of information that might assist you in incorporating all that information. So you are set to do a redox pogel. Now, redox is two words combined together. It's reduction and oxidation. What we're talking about in these reactions is the transfer of electrons. And you guys, this is how we make a battery. If you were to open up a battery, what would you see? Chemicals. And we'll get into more about how batteries actually work later, but right now you just need to understand that you have two processes always occurring and they go together. You have oxidation and you have reduction. Now, I like to remember them with oil rig. I know Mrs. Gersbowski likes to do Leo Gur. Leo the lion says Gur. I like oil rig. Oil stands for oxidation is loss of electrons, and rig, reduction, is gain of electrons. Oil rig. Oxidation is the loss of electrons, reduction is the gain of electrons. So if you're losing electrons, you're going to find the electrons as products. If you're gaining electrons, then you're going to see them as reactants. And you got to think about the charge on an electron. Electrons are negative, right? So if you have a bunch of negatives on your body and then you start losing electrons, somebody starts taking them off, won't you become more positive? But then somebody starts dumping the electrons onto you, your poor little body, you're going to become more negative, and that's reduction. So if you just think about that, that kind of helps out. So what you're going to be asked to do first on this POGIL and in an assignment is to assign oxidation numbers. Now, they are not necessarily the same as what's on the periodic table, because I know that S is in column 16, but believe it or not, sometimes sulfur has a +6 charge. I know, weird, crazy, right? Let's talk about why. And in the book are all of the rules. Go look at the book and look at the rules. But here they are kind of in a nutshell as we go through some examples. In this example, you'll notice that zinc doesn't have a charge at all, and it's a solid. Well, isn't that how we find zinc in nature? Yeah. Anytime you have an element in its natural state, we assign it an oxidation number of 0. So you'll notice that copper is also in its natural state, okay? So that will also have a 0. Now, if it is an ion like these two, well, that's its charge, okay? That's it. And notice when we write the oxidation number, don't ask me why, I really have no idea. The plus and minus goes before the number, but when we write it like this in the formula, it's backwards. So those are pretty easy. In its natural state, give it a 0. If it's an ion, that's its charge. All right, now this equation's a little tougher. Oh, and by the way, this equation, you should be able to look at this equation and immediately know it's redox. You know why? Because clearly that's a 0. Clearly that has a +2. And when the charge changes, you have redox. Let me repeat that. When the charge changes, you have redox. Okay? Now, if you look at this equation, you're going to be like, yeah, there's no charge. There is. This is iron in its natural state. We assign it a 0. Oxygen that we breathe, that is the natural state. It gets a 0. Now, you guys know that anytime you have a compound, one side is positive and one side is negative. Clearly, iron and oxygen have to have a charge on this side. So another easy way to see redox, besides the obvious like, oh, it has no charge, now it has a charge, is this. When they are alone, and then when suddenly they have a partner, you're going to see a change in the charge. All right, so how do you do this? How do you find the charge of these two? Well, one of the rules is the one that is more electronegative gets its charge from the periodic table. Recall, fluorine F, number 9, is the most electronegative, followed by oxygen, followed by chlorine, in that order. Fluorine, oxygen, chlorine. So clearly oxygen is more electronegative. So we're going to assign it a value of -2. So each oxygen has a charge of -2. But guys, there's 3 of them. So this side of the formula seems like -6. Well, the other side has to be a +6, right? But we have 2 elements. So that means each one is a +3. So when you go in this direction, you multiply. When you go backwards, you divide. So if each one is a -2, multiply it by 3, and you get a total charge of -6. So this side has to be a +6. They got to balance out. Remember, this is like months and months ago, writing formulas. But there's 2 of them, so when you divide, each one must have a charge of +3. So we say this is a +3 and this is a -2. All right, let's go to the next one. All right, let's tackle the really easy ones first. Well, gosh darn, it's got a charge, so we know that's going to be a +1. Ooh, +2. Ooh, +3. Oh, those are easy, right? All right, let's tackle water next. It's always going to be the same. Well, who's more electronegative? Oxygen, it gets the -2. So this side acts like -2. So this side, right, has to be +2. But there's 2 of them, so each H is 1. Now, guys, most of the time, oxygen's going to be a -2. Most of the time, hydrogen will be a +1. There are rare occasions where oxygen will be a -1 and hydrogen will be a -1. But 99% of the time, hydrogen +1, oxygen -2, almost all the time. Now, I want to show you something else too. Water is neutral. So these charges have to add up to 0. Which they do. Perfect. All right, let's tackle this thing right here. So we know oxygen's going to get the -2. -2 times 2, this side is -4. This side has to be a +4. But there's only one of them. So manganese is a +4. Now, this one's a little different. Because it has a charge, the entire thing has to add up to -1. Well, we know oxygen's a -2, right? -2 times 4, this side acts like -8. Well, what does this side have to be? What minus 8 is -1? +7. That's right, manganese can be a +7. +7 minus 8, you get a -1. All right, so one thing I would like to point out, and this is something I've learned as I've gone through my graduate degree, is chemistry is complicated. Like if you find Mn on the periodic table, it's a metal. O, non-metal. So what did we learn before? Oh, a metal and a non-metal is ionic. Not in this case. Whenever that charge gets to be +4 or greater, it actually acts more covalently than it does ionically. I don't know, weird, complicated. So anyway, that's how you do the oxidation numbers for that. Now, while we're here, I want to point something out. One of the things we're going to do is try to figure out, well, who changes? Well, take a look at this. Don't those 2 change? Iron goes from a +2 to a +3. It's becoming more positive. And when you become more positive, it's because you're losing electrons. If your charge is becoming more positive, you're being oxidized. If your charge becomes more negative, you're being reduced. So we can say that, oh, iron is being oxidized. It's losing electrons. Well, who's being reduced then? Oh, look at that. Mn went from a +7 to a +4. It got reduced. And if that doesn't make sense to you, let's think about your bank account. You have $100. It just got reduced by 50. You have 50 bucks left. Didn't it decrease? Didn't it become more negative? There you go. All right, let's tackle one more. And by the way, these are all from the very beginning of the POGL, so you can go back and work on that. Now, very easy. We know it's going to be a -1. I don't even have to think about it. And oh, there's no charge. That must be a 0. Piece of cake. Oh, now we have ions. So let's tackle this ion right here, okay? SO4. for -2. We know this needs to add up to -2, okay? So you look at the periodic table. O is more electronegative, so it's going to get the -2, but it's going to seem like -8. Now notice I'm doing the seem like down here. The charge is a -2, all right? It's not -8, it's -2. It's just that there's 4 of them, so it seems like -8. Well, think about math. What -8 is -2? +6. Sulfur is a +6. So sulfur is a +6, oxygen's a -2. You might want to memorize sulfate. Sulfate is always going to be +6 -2. Always. And we do sulfate a lot, so you might just want to memorize it. All right, well, let's tackle this ugly thing. We have S2O8 with a -2. Oops, I wrote that backwards. So we know it has to add up to -2, right? Well, guys, you know that oxygen's going to be a -2. That's going to be a -16. What -16 is -2? A +14. But there's 2 of them. So do some division. 14 divided by 2 is a +7. So this is going to be a +7. This is going to be a -2. So now you can look and see who changed. Well, iodine went from a -1 to a 0. You owed me $1. Now you don't. Aren't you moving in the positive direction? So that's oxidized because it becomes positive. Meanwhile, look at the S. The S went from a +7 to a +6. It's becoming negative. That is reduction. Okay? All right. Let's tackle one more. So we've talked about sulfate. That's one that you really should just memorize. It's always going to be +6, -2, always. Another one you're going to deal with a lot is nitrate. So it's nice to just kind of memorize this one. Now, you can do PbNO32 a couple of different ways. I'm going to show you the way I like to do it. Well, clearly this formula is divided between lead and the nitrate, right? Well, if you go and look at your polyatomic ion sheet, we know that nitrate is a -1. So if this is a -1 and there's 2 of them, doesn't this side have to be a +2? Yeah. Okay, so that was easy. We know lead is going to be a +2, but let's deal with this nitrate. I really don't like to deal with the whole formula. I just want to deal with this ion. I know it needs to add up to -1. I know oxygen's going to get the -2, so that's a -6. What? -6 is -1, a +5. Nitrate will always be +5 and a -2. I just have them memorized. It makes life easier, okay? Now later on, they're going to give you the following equation, and all you're going to see is this. I2 becomes 2I negative. They want you to add electrons to the correct side and then decide if it is oxidation or reduction. So the first thing I want you to notice is you do have the correct number of I's on both sides. There are 2 here, there are 2 here. You still have to conserve atoms. Here's where it gets fun. We also have to conserve charge. Now on this side, there is no charge. But on this side, there's a -2 charge because 2 times -1 is -2. So we need to make both sides have a -2 charge. The only thing you're allowed to do is add electrons. It doesn't make sense to add electrons to this side because I'm just going to make this even more negative. So clearly I need to add electrons to this side. But if I only add 1, that only makes this -1. Remember, electrons are negative. So I need to add 2 electrons to make this side be -2. So think about what we're doing here. We are gaining or adding electrons to that. Therefore, this is reduction. Remember, oxidation, it'll be on the other side. Now, this one down here is kind of tricky. Okay, you have to kind of figure out who is changing here. And who is changing here is going to be the chlorine. Obviously, this isn't a full thing. They didn't give you both oxidation and reduction. They were kind of sneaky, I know, right? But I want to show you what's going on with this one. And this is number 11, by the way. 11, the fourth one on your worksheet. So what do we know about this? We know that oxygen is going to be -2. That's going to be a +1. That's not changing. What's changing is this chlorine. So we have a -2 here. So this side is a -4. What does that side have to be? And remember, they're going to add up to a -1. All right, so this is a +3 because +3 minus 4 is a -1. So I know the chlorine is changing over here. This is a -2, so it seems like -6. So this is going to be a +5 because we need it to add up to -1. I know I'm going kind of quick here, but let's look at what happened. This goes to that, right? So it is increasing by 2. So don't I want to now decrease this by 2? And this is oxidation. I know that was a tricky one. That one was mean. I wouldn't normally do that to you. Normally I would do that one with you guys. Now, later on question, oh, where am I, y'all? On question 14, actually question 12. Question 12 wants you to go back and show that if you take the two half reactions in Model 2, by the way, what's a half reaction? A half reaction is where we split up the overall reaction. Notice this just has to do with zinc. This just has to do with copper. Notice this is oxidation because we're losing electrons. This one is the reduction. They want you to show that you can add these up and get the overall equation again. Well, in algebra, if this is on this side and this is on this side, it's going to cross off. So when you add it up, this is what you get. And guess what? You get your equation back, okay? Now, in 14, you are asked to show how two different reactions, and I believe they're models C and D, how did these add up to get that overall reaction? Well, before we can add these up, I need you to notice that our electrons are not conserved. In redox, electrons have to be conserved. They have to balance out. So we're going to have to do a little manipulating here. We're going to need to multiply that whole equation by 4 and this one by 3 so that those electrons will cancel out. So we're going to get 4 irons makes 4 of these and 12 electrons. Meanwhile, multiply by 3, we get 3O2 plus 12 electrons makes 6O2 negative. Now can we add them up? You bet you. Those are going to cross off. So what is left? 3 oxygen plus 4 Fe. And we'll spend some time doing a lot of this fun stuff. Okay, you guys, balancing these half reactions and all. It's a process, but it's fun. Now, if you go back and look at the equation, they don't list this. They listed 2Fe2O3, and they are equivalent things if you think about it. If I have 4 irons, give me a moment to write these, you guys, and 6 oxygens, I'm going to run out of room. How do you make an Fe2O3? Fe2O3. And then Fe2O3. So these ions really do make 2 of those compounds, but it is equivalent. The point here is that in redox, not only do our atoms have to be conserved, but charge is conserved and electrons are conserved. Now that's all I've got for you on that worksheet. Try it. I'll be back tomorrow. I'll be there to help you guys out, but try to get these rules down and how to assign the oxidation number. And by the way, when you've got something in the middle, like, I don't know, let's do like HClO4 and it's a negative. All right. This can get kind of tricky because students will be like, how do I split this up? We need to look at each piece, okay? We know oxygen is going to be the -2. It's way more electronegative than chlorine, but it's going to seem like a -8 here. And I told you that hydrogen almost always gets its +1. So what makes this statement true? Well, 1 plus 6 gets you 7 Take away 8 gets you -1. So this is going to be a +7. Usually that thing in the middle is weird and it's not going to reflect the periodic table at all. But we're going to practice more of this. We're going to practice it when we do homework number 1, as we balance half reactions. We will use this information throughout this whole chapter. And lastly, we're going to see how batteries work. Batteries are really, really, really cool. We're going to do a cool experiment with it, and it'll pull everything together. So hang in there. I know it's totally new, totally different, but you guys got this.